Hello, welcome to PhysioDesigner tutorial series. In this tutorial series, we are going to create a model of human upright posture control. On PhysioDesigner, we are going to use Gaussian noise in the model, which requires a special treatment on the numerical integration. Besides that, time-delayed feedback will also appear in the model. These modeling techniques can be applied other occasions. Okay, let's begin with a background of the human postural control. During quiet standing, do you think you are stopping completely? Actually no, it is known that we are always fluctuating a little bit. The time course of the antero-posterior tilt angle of the body from vertical shows clear fluctuation as the graph in this slide. The source of the fluctuation is one of hot topics to discuss. For a long time, it is thought that the upright quiet standing is stabilized by the high joint stiffness caused by tonus of muscles around ankle. But recently, a new control hypothesis was proposed, in which brain acts more important role. The control signal from brain switches the on-off of muscles activity. Hence, the upright posture is no more asymptotically stable, but the state point is controlled to be near the upright posture. We will examine both control strategies by simulations in this tutorial series. The upright posture can be modeled by an inverted pendulum. The tilt angle from vertical is denoted by theta. The height from the ground to the center of body mass is assumed to be 1 meter, and the weight is 60 kilograms. Then the motion equation of this inverted pendulum is denoted by this equation. Here, I represents a moment of inertia, and g, the acceleration of gravity, whose value is 9.81 meters per second square. This equation shows a free fall of the inverted pendulum. But, actually, this equation is valid only for small theta, because sine theta, which is supposed to appear in the right-hand side of the equation, is already approximated by theta for simplicity. To prevent the inverted pendulum from falling, we need to add the control torque working around the ankle to the right-hand side of the equation. We will consider 4 models in this tutorial series, each of which considers different type of the ankle torque T. Before going to explanation of those models, let's derive 2 first-order ordinary differential equations from the motion equation to make a model. Let's introduce a new variable w, which is defined as a first derivative of theta. Then the motion equation can be rewritten as an equation with the first derivative of w. Now we have 2 ODE shown in the slide. At first, let's create this model on PhysioDesigner, and later we will consider to implement the ankle torque. Let's create a module. Right-click on the main white canvas, and select Make Module in the context menu. Input its name. Any name is okay. Here, I put inverted pendulum, and right-click on the new module, and select Edit Physical Quantity. We will create the equation for theta. At first, select Stated the Type combo box, and set name theta. Move to the Initial Value tab to check. Its initial value is set to 0 by default. Move to Implementation tab. Input the equation at the bottom text box. It is diff theta time equals to w. W is not defined yet, so the system asks you if you want to create an entry for w automatically. Click Yes button. Next, select W in the table, and move to Basic Setting tab. Now the type is static parameter. Change it to state. Check the initial value, it is 0 again, and move to Implementation tab. This time, the equation is mgh theta minus t over I. These physical quantities are not defined yet, so it asks again. Click Yes button. Select M in the table. This time, M is a static parameter type physical quantity, so we don't need to change the physical quantity type at Basic Setting tab. And set 60. Similarly for G and H, the values are 9.81 and 1, respectively. For T, for now we can leave it as t equals 0. It means there is no control torque around the ankle. Later, we will implement the torque t considering neural feedback. Finally, select I in the physical quantity table. I is again static parameter type, and its value is m times h square. Alright, we finished to define physical quantities. Click OK button, and close the dialog. Before trying to check the dynamics, let's set some properties on time unit. Right-click on the white canvas, and select Edit Model Preferences. Go to Numerical Config tab. Select second at combo boxes for time unit in the default time discretization configuration, and for simulation time span, and click OK button to close the dialog. Then let's set the initial value of theta as 0.01. Save the model, and call Flint for performing a simulation. As you expect, the values of theta and w diverge to infinity, and such values don't make sense, because they are already out of the assumption. The model is valid only for small values for theta and w. But anyway, it is clear that the inverted pendulum fell down. Let's implement the ankle torque to control the upright posture. We can consider 5 types of torques. There are 2 torques, denoted by k theta and b theta dot, which come from the intrinsic mechanical impedance with passive stiffness and with passive viscosity, respectively. And there are 2 torques, denoted by fp and fd, representing the active neural feedback torques determined by delay-affected tilt angle, and by angular velocity, respectively. At last, there is noise torque modeled by an additive Gaussian white noise of intensity sigma. For the Model 1, we will consider very simple PD feedback torques to control the inverted pendulum. Namely, for the intrinsic mechanics-related torques, we use K equals 471 Nm per radian, and B equals 4.0 Nm/second per radian. We don't consider time delay for neural feedbacks. Hence, delta equals 0. The neural feedback determined by the tilt angle is, simply, p theta, and the feedback by the angular velocity is d theta dot. The parameter values are p equals 0.8 mgh Nm per radian, and d equals 270 Nm/second per radian. We also don't consider the noise torque in this model, hence sigma equals 0. Now, let's implement the ankle torque on PhysioDesigner for Model 1. Open the physical quantity dialog, and select the torque T in the table. Change the type to variable parameter. Move to Implementation tab. The equation is T equals K theta plus BW plus FP plus FD plus noise. These physical quantities are not defined yet, so there is a dialog popping up. Select Yes button to create those physical quantities. Let's set parameter values. K equals 471. B equals 4.0. FP must be variable parameter type, and its implementation is Fp equals P times theta. Fd equals D times W. Don't forget to change its type to variable parameter type. Just let's confirm that noise equals 0 in this model. P equals 0.8 mgh. And D equals 270. That's all for the ankle torque setup. Close the dialog. Let's save this model as Model 1. So, select Save As in File menu. Now, let's run simulations. Call Flint and click Run button. At first, let's observe the time course of theta. It asymptotically converges to 0, which corresponds to converging to the upright posture. The orbit on the theta W plane also converges to the origin by making a curve. Let's observe the behavior with different parameters. Firstly, let's try to use larger value for p, which is a coefficient of neural feedback proportional to theta. In this case, you can see there is a little overshoot in the time course of theta. On w theta plane, the orbit makes spiral in the vicinity of the fixed point. Next, oppositely, let's use smaller value for p. The convergence process becomes slower, and there is no overshoot in the time course, nor spiral on the w theta phase plane. If we use even smaller value for p, what happened? The upright posture became unstable, and the theta diverged. At last, let's try to use smaller value for d, and set the original value to p. In this case, again there is the overshoot in the time course of theta, and you can see the clear spiral on the phase plane. Please notice that the larger value of p causes fast movement toward the fixed point, but instead of that, it causes overshoot and oscillatory response, which is also induced by smaller value of d. If p is too small, the upright posture lost its stability. The stability can be analyzed by examining the eigenvalues of the system. If both of eigenvalues, or real part of them, are negative, then the fixed point, corresponding to the upright posture, is asymptotically stable. As you see, for large p or small d, eigenvalues can be complex number, causing overshoot and spiral orbit, and for small p, the eigenvalues can be positive, meaning the fixed point becomes unstable. That's all for this tutorial. In the next tutorial, we will introduce the time delay in the PD control. Thank you for watching until the end. Hope to see you next time. Bye-bye.